All right, our very last video for Units 9 and 10 review. Number 21 to 27. So here's number 21. We've got this about the time spent putting water in the pool and how much gallons is in the pool. So here is our slope, our standard deviation of the slope. Here's our standard deviation of the residuals. Remember, S of the E equals the S, standard deviation of residuals. Okay, because we're interpreting some of those things here at the first. What's the slope? Well, that's that 0.63383. State it and interpret it in context. Okay, so there's our slope. For every one increase in the x, the predicted y, it does this. Interpret the slope. So for every additional minute, the pool is filling with water. That's the every one increase in the x. Okay. The water in the pool, that's the y, is predicted to increase 0.63 thousand gallons. Okay, and that's because up here, see, look, this is gallons in thousands present in the pool. Okay, so that's what units we're pumping them in. Well, that's 630 gallons. Okay. Next, 22, state and interpret the standard deviation of the residuals. That's the errors. The little e here, S with the little e, is that standard deviation residuals here. So this is saying, remember our little, the average amount that the actual y. Okay, so that's this. The average amount that the actual water in the pool varies from the predicted water in the pool is 9.282 thousand gallons. That seems like a lot to me, 9,282 gallons. But yeah, I don't know. Maybe this pool is like gargantuan, and so that's not really that much variation in what's actually in there versus what's predicted to be in there. Okay, next, state and interpret the standard error of the slope. Well, that's this number here next to the slope, 0.07039. So I stated that. Okay, so remember, if you sample many times, so if we sample many times, I'd expect the slope you find of the relation between the time, the filling time, the amount of filling time in minutes, and the water in the pool that varies about 0.07039 thousand gallons per minute. Okay, so let me read that and not sing it to you. If we sampled many times, then I'd expect the slope of the relationship of the filling time in water to vary about 70.39 gallons per minute. See, I like that. That kind of makes a little bit more common sense to me than 0.07039 thousand gallons. So again, remember, communication is key. That's your value as a human statistician, not just a machine spitting out statistics, is that communication component of contextually what is happening. All right, so is there evidence of a predictive linear relationship? So beta is the slope of the relationship between the filling time in minutes and the water in the pool. And our null hypothesis is that that's 0. Alternatively, it didn't ask us one or the other, so I just did two-tailed. Let's see. So linear regression. Oh, okay. Linear regression t-test. Okay. You know what? I started doing this and I started doing all this work, and it turned out that I did not have to do that work because that output, the computer output, includes the t-score and the p-value. So that's a good point to use common sense and notice, look, it was left in this time. I didn't have to compute it myself. Now, when I computed it myself, woohoo, I did get 9. So 9 is the t-score with a p-value of 0. Now, interestingly enough, Do I know the sample size? I don't think I had told it had been told to us, and I guess I didn't really need it, but this was AP. I'm sure that would have been college board test would have been given to you. All right, low p-value. So I reject HO. So there is evidence of a linear relationship, a predictive linear relationship between the filling time and the water in the pool. Makes sense because I think that's going to be a pretty constant rate. All right, 25. Here we have this situation that we were just studying. It was about, look, it told me about they took a sample from the over 40 age group and a sample from the under 40 age group. So that's two separate populations. They took a sample from each, and then they were having these categories, one variable amongst that. That's a homogeneity test. Number 26, let's see here. So this was about photographers, and they had a situation where there had been a claimed, let's see where I can find that. There had been a claimed rate. So they did a chi-squared goodness of fit using the null hypothesis that the magazine's claim of the percentages of certain types of photographers is correct. So the null hypothesis, the claim is correct. The alternative, of course, is that the the magazine's expected rates are not correct. So claim is incorrect. All right. I did this 4.19. I TCDF'd that 4.19 to 999 with 2 degrees of freedom. Now, why 2 degrees of freedom? Because this is a goodness of fit problem. It has 3 categories. So categories minus 1 is the degrees of freedom for chi-squared goodness of fit. So that gave me that p-value 0.123. Well, that I would fail to reject the null. So I do not have convincing evidence that the manager's claim is incorrect. All right, and the last one. Ooh, this is a good one. I gave you this problem as kind of like a bonus question I remember in an earlier unit. So this one's kind of cool. We're talking about the telescopic black umbrellas. And so what's interesting is that we are asked, what is the expected number? If we know that, and I had posed it to you back when we talked about independence, meaning that it needs to happen at the same rate. So I need to find out what rate are the black umbrellas in the sample. So I had to first step, come up with this number. So I 300 minus those things to get 186. All right. Then I could get this telescopic number right here. I needed this here. Now, keep in mind, that is the actual number, not what's expected. This is the number that everybody on that test, it was a bonus question nobody got, because everybody at that time wanted to tell me it was E. That's a trick answer, because that is the closest to the actual number of black telescopic umbrellas, not what it asked for, which was the expected number of black telescopic umbrellas. Now, remember with our matrix, we have the expected is that row total times column total divided by the total total. Well, see, look here. We had just gotten that row total, 186. So now get that column total. Now that I put this 128 in here, I got this column total of 188. So I now have row total times column total divided by the total total. And that is then how you actually get 116.56. So it's closest to D is the answer. Okay. The key was expected versus actual. So that's, a lot of the things that we're doing in this class is the sample versus the population, the actual versus what's expected. Okay, so we're always keeping those things straight so that we know where we are in statistically what's happening. Okay, that's it. So good luck to you on your units 9 and 10 test. chi-squared, and linear regressions.